Today I'm gonna make you learn how to implement the 2-bit comparator and simulate it in the Proteus as well. So here, as you can see that it takes the I've just made the rough diagram. It takes the 2 bit input value from here and compare these values whether it's equal or greater or lesser than BB. So this comparator will compare the value and give you the output from here side, and the higher logic state will show you that the particular function is executing or not. So we use the Karnaugh map. It's generally known as K-map. So this is the technique that is used to make the circuits in Proteus by the help of the equation by using AND gates or NOT gates. So this is the Karnaugh map. As you already know that this is A1 dash A, this is A naught dash A naught, and this. So here are the Karnaugh map for A1 A naught equals to B1 and B naught. So as you can see that there are only one, so I can circle it in this way, and you should watch it from here. So let's suppose I'm just solving this. So watching it from this side, it is A1 dash, and from this side it is A naught dash, and from this side it will be B1 dash, and from this side you can see that its value is B naught dash. So generally dash is a complement, so all you will repeat the process by these 4 values, and you will get the 4 different types of uh, values. So it forms a 4 terminal AND gate, and all these 4-bit terminal AND gates will be joined by the 4 terminal OR gate. So here is the Karnaugh map for A1 A naught equals to B1 B naught. So I've made another Karnaugh map for which A1 is lesser than B1 B naught. So here is the Karnaugh map for this one, and I've circled these values like this and this one. So this one will be connected to the this one. So let's do it. So first watch from this side. His value is A1 and this value is A naught, and here it is coming in the 2 regions where B1 and B1 dash is present, so this will cancel each other's effect. So here you can see that the output equation will be generated like this. Same here is going on for the graph of A1 A naught is greater than B1 B naught. So as you can see that generally these ones are made when you compare these graphs in the form of matrix, just like this. This is the values of B1, and this is the value of A1. So you should compare it 0 0 0 0 is equal, it means that it's not greater, then it will be 0. 0 1 means A1 A naught is greater than B1 B naught, so here it is 1. Same is the process will be repeated throughout the map, so the equation is generated like this. So let's move on to the Proteus. So here I'm using the logic toggles for that, and name them A0, A1, B0 and B1 respectively. So first I'm going to make the circuit for A0, A1 equals to B0, B1 when both the 2-bit values are equal. So here I'm just writing this equation like this one and this. Here as you can see that this equation is here that I've made from the Karnaugh map. So A1 complement, A naught complement, B1 naught complement and B naught complement. So I've used the NOT gates for the complement and then joined all these 4 values of the input with an AND gate. So moving on to the next value of this one, we have connected like this one. Simultaneously repeat the process and just combine these values. If there is no any complement, then you can combine this from the NOR gate, from the after the NOT gate, and if there is the complement appearing, then you can combine it before the NOT gate. So here as you can see that I've started the simulation. As you can see that when both the input values are equal, then the LED get turns on. So first I'm just making this circuit for A1 is lesser than B not B1. So here's the equation, and I'm combining according to the equation, just like that and that. So here the circuit is completely done by the help of equation. Now I'm going to make the circuit for A1 is greater than B1 B naught. So this circuit is also implemented with the help of equation as well. So as you can see that the proper circuit is made and simulation is going on, and you can see that when both the 2-bit inputs are equal, in the first LED get turned on, and when A1 A naught is lesser than B1 B naught, then the second LED get turned on, and when A1 A naught is lesser than B1 B naught. Learn how to make the BCD to 7 segment circuit. Actually, the 7 segment circuit consists of these segments that are 7 in the number, and these are the digital LED displays that you will most probably see in the markets as well. So while implementing this, we have to first make sure that we have made the table. So these values just go from 0 to 9. So you can see that here it is 0 and 1 will be in this state when the B and C LEDs are burning, while the all other LEDs are turned off, and the 2 will be displayed only in that situation where the C and F LED will be turned off. So these are the logic states where the 0 and 1 makes a sense. So here I have made 0 1 0 1 0 1 0 1, and there are the total number of 10 values from 0 to 9, and 0 0 1 1 0 0 1 1 0 0 1 1 0 0 0 0 1 1 1 1 and 0 0. So you can make the values like this. So as you can see that at the first logic state, when the 0 will be printed, so the G will turn off. So here is the 0 logic state when the G is turned off and all the LEDs are on to print the 0. So after that I have to print 1, so B and C will be turned off. To print 1, then B and C will be turned on and all the other LEDs will be turned off. So you can see that 1 and 1 logic state is appearing in B, and all other LEDs are turned off. Same is the process with is repeated with all other logic state. For example, if we have to print 8, then all the LEDs will be turned on, neither LED will get turned off. So here you can see that in the 8 logic state, all the LEDs are at 1 logic state. In the previous question number 1, in which we have studied the 2-bit comparator, the process will be same like in the previous question, but I have to show some difference, that is here. As you can see that here is the Karnaugh map for A, and this map is for B. So in order to make these 0 and 1 states, you have to study the tables. In a logic state, there is 1 0 1 1 0 0 1 1 1 1. So this graph will be same as the comparison, where the 0 0 and 0 0 box will fill the 1, and 0 0 0 1 box will fill the 0, and 0 0 1 0 box will fill 1. So here you can see that 0 0 and 0 0 box is filling this. So from preceding upward to downward, 1 0 1 1 0 1 1 0. So here you can write as 1 0 1 1 0 1 1 1. Then this column will be 0 throughout the process when A B C D E F G LEDs come. So the next one will be 1 1 0 and 0. The same process will be repeated for this LED B. You can see that 1 1 1 1 1 0 0 1 1 1. So here it is 1 1 1 1 1 0 0 1, then 1 1 will come. All the other logic states will be 0. This is the fixed 0 states because 1 1 and 1 0 column are not coming here, because this can increase the number, and here is the empty logic state because we have to move from 0 to 9. So here is the equation, because you can make this as well, this circuit, and this way and this way. So as done in the previous question, you can make the C equations, and this is for the D equation, and this is for E, this is for F, and this is for G. So let's move on to the Proteus to implement these equations and convert them into the circuits. So here I am picking the logic toggles and the different components like 4, 3 and 2 terminal AND gates or OR gates from the library. So I am putting the NOT gates here to make the B complement, and using the simple wire to make the A, B, C, D inputs. So now I will solve the circuit for A. By using this equation, it seems to be quite very easier when you make the circuit like this. Now go towards the B. Same process will be repeated, but the equation is changed. So I am again highlighting the uh, terminals in order to have less difficulty in finding the wire of particular. So here is the circuit for C, and then I will use the circuit for D. You can also reduce the speed of the video to correctly examine how I'm making the circuit. Well, this is for D, and now for E. Actually, all these equations are from Carnot map that I've previously discussed with you, and this is for F, and the last but not the least is G. So I'm going to make the circuit for G. Look here, and this is for G. After combining all these gates from the OR gate, actually the plus symbol uh, signifies the OR gate. So after making all this, I will pick a 7 segment LED display. You can also pick anyone, but the best LED for you that is working with these logic gates is a green LED display. So here is that one terminal here, as you can see upward, is the grounded terminal, and the other 7 terminals are A, B, C, D, E, F. So I'm combining all these terminals with the LED like this one, and B with this one. Actually the wire does not override with the writing fonts, so I will make the suitable assumptions or suitable things to make the wire to be connected like that. So here is this, and then comes the F terminal. Well, here is this, and then remain left there is G terminal. So I'm just combining this like that. A step-by-step process is quite easier, so you can pick from the probe mode and then ground it. So let's change the color of the LEDs. So as you can see that when all the logic states are 0, it's printing 0, and when sorry, so here is the 0 when only the D is 1 as shown in the table, so it will print 2, and when 11 then it will print 3, and when 100 it will print 4, and then it will print 5 at 101, and triple one it will print 8, and then it will print 6, and then it will print 7 and 8, and then 1001 9. I hope that you will really enjoy this video and understand the basic concept of ICs and the digital displays. Thanks.